This lecture is in continuation to my first lecture on basics of remote sensing. In the first lecture, we had discussed about the definition of remote sensing, the type of platforms placed near to the earth, placed on the aircrafts, and then the spaceborne platforms. Then how this technology is useful to the mankind, the different scientists of different fields as well as the social scientists. We had also discussed about the electromagnetic spectrum, how it originates following the various rules of physics from the sun and the earth, how these electromagnetic radiations interact with the different components of atmosphere and earth material. Then we had the characteristic reflectance curves of vegetation, water and soil. In the end, I had given a brief introduction regarding the spectral signature and spectral pattern. Today I'll try to go in a little more deep into this spectral pattern and spectral signature. Now we have the reflectance characteristic curves of soil based on the soil texture. Now we can see that all these three types of soil, right from very fine sandy loam, and sandy loam, they are showing almost the same pattern of reflection as the material interacts with different parts of the electromagnetic spectrum. Say in the visible part, the reflectance is around say 10%. As they come to around say 1.25 micrometer wavelength, so when the 1.25 micrometer wavelength interacts with these types of soil, it shows the peak reflectance. The very fine sandy loam, it shows around 20% of the wavelength being reflected. Then all of them, the three types of soil, there's a sudden reduction in the reflectance at around say 1.4 micrometer wavelength. You must be remembering that we had discussed regarding the absorption by water vapors at 1.4, 1.9 and 2.6 micrometers in our earlier lecture, and see you can see that at 1.4, then again at 1.9 and then here 2.6, there is a sudden drop in the amount of reflectance because of those water vapors in the atmosphere. So overall the pattern is the same. They are showing peak reflection at around 1.3 or 1.25 micrometers, then they drop in reflection at 1.4, 1.9 micrometer length. So if we observe, so here whatever is the amount of reflection is the spectral signature of very fine sandy loam. Here this is the spectral signature of fine sandy loam. Then we have, but the pattern of all of them is almost the same. So this spectral signature will depend upon a lot many things, about on the availability of the sunlight on the surface of the reflecting object, but the pattern remains the same. Similarly, if we see this again, we have the different clay and sand. Now if, for example, again here we see that they have uh, both the clay with 2 to 6% of moisture, and with 35 to 40% of moisture, they show peak reflectance at around, say, 1.25 micrometers. Again, they have this sudden drop in the reflection at 1.4 and 1.9 micrometers. But the pattern of both of them remains the same. The signatures may be, here the reflectance is say 15%, here the reflectance is 50%, but the overall pattern remains the same. So these patterns are helpful in identifying the type of object or type of material. Here again we have the different very coarse sand, medium sand, fine sand, very fine sand, medium sand, and you can see that at around 0.55 micrometer wavelength there is a sudden change in the reflection pattern as you move from beyond this wavelength. So all of them are having different signatures, reflectance signatures, but the pattern is same. We had also learned that the different objects interact differently with the different parts of the electromagnetic spectrum, and uh, using this analogy we are able to distinguish between some of the features which otherwise are indistinguishable in particular wave band, but they can be differentiated in case of in case we view them in different wavelengths or wave band. Now here I take this Google image which we are all very much familiar nowadays. So this is some rural area where we have different types of landforms like the settlement, village settlement. Here we have got the orchard, this is all orchard again, here it is, and then we have got the agricultural fields spread into this region, and also some unmetalled roads here at this place. So these are some of the features which we are identifying on the basis of their reflectance. Now you can see that these are different crops they are growing because we are seeing different reflectance pattern of the different parts of the electromagnetic spectrum. Of course, some other parameters are also used which we'll be discussing later on. Now we take up a black and white satellite image of a similar area where we have the agricultural fields, the settlements, the roads, etc. Now any image, it is made up of very fine cells which are known as pixels. Now again the same image is here. Now suppose I keep on enlarging this image. I have taken up this area. Now this has been enlarged, further it has been enlarged, and now this portion has been enlarged. So if you keep on enlarging, then we say that the image pixelates, it has got pixelated. What does this mean? This means that if we keep on enlarging it, we are able to see the cells of which it is made up of. Now these individual cells henceforth called the pixel have their own reflectance values, and you can see that if we are viewing this area, this is a cell which is appearing very white, or and this one is appearing as almost black, and the others are showing the different shades of gray. Now we know that higher the reflectance, lighter would be the tone of the gray, and vice versa. Looking at the zoomed part of the image which I showed you just now, we'll try to define what is a pixel. Pixel, or which is an abbreviated version of picture element, it is the smallest unit or the cell of an image displayed on the screen. In this image, it can be noted that each of the cell or the pixel has a characteristic reflectance and is depicted by the digital number value varying between 0 to 255. Now you can see that here each of these pixels are having different tones of gray. Here it appears to be almost same. To our eyes, we are not able to differentiate between the different shades. However, digitally it would be possible that each of these pixels will be having reflectance which may be different very slightly. Now here it has got pixels which are relatively showing a very bright tone, and then you have pixels which are showing darker tones. Thus, the larger the number of pixels in an image, that is, more cells showing very fine difference in reflectance or the DN value, the better will be the quality of the image. So image having larger number of pixels or cells with different varied reflectance values or the DN numbers will be of a better quality. Our eyes at best can differentiate almost 16 levels of gray in a black and white image. However, digitally we can differentiate 128 or 256 gray tones, which are known as the gray values. Each of these gray values are given a digital number or the DN value. For maximum reflection, the DN value is 255, and for minimum reflection, the DN value is 0. Now for very minor changes in the gray tones which our eyes cannot perceive, the percentage of reflection the gray values or the digital numbers keep on changing. Thus, a black and white image can have DN values ranging from 0 to 127 or 0 to 255, depending upon the radiometric resolution of the sensors which are there. We will be discussing about this radiometric resolution later in the lectures. Now again I have taken the same zoomed image where we have taken a 6 by 6 grid of pixels. Now in this 6 by 6 grid, the corresponding digital numbers are given, and this cell which shows maximum reflection has a digital number of 250, whereas this cell, which is showing minimum amount of reflectance, or we can say it is black, it is showing a reflectance value or the DN value of 42. Now in this you can see this part of the image, the gray values are changing very slightly, and these are depicted by the digital numbers here. Now if we take these two individual cells, our eyes are not able to differentiate between the two. However, the DN value of this keeps on changing from, say, it is different from 182, 183, here it is 142, 143. We cannot otherwise differentiate between these two pixels with our eyes. Similarly, this one is showing having a reflectance value of 42, whereas this this pixel, it has the value of 62. So the quality of image depends upon the number of pixels per inch that makes up that particular image. Now we'll try to understand how the quality of the image improves with the decrease in the size of the pixel. Now I have taken this example, taken this some pixel having a digital number of 105, and the size of the pixel is 100 meters by 100 meters. That means for 100 by 100 meter area, the average reflection shows a digital number of 105. Now if I divide this 100 by 100 meter area into 10 by 10 meters pixels, then there would be 100 pixels, and now each of these pixels will be having DN values which may say range between 114 to 95. That is, it is not that each of the 100 pixel will be having DN value which is denoted by 105. Now again I have divided this, taken this one of the pixels having DN value of 102. It is further subdivided into 10 by 10 pixel is divided into 10 units of 1 meter pixel size, 1 square meter, that is 1 by 1 meter, and again there would be 100 pixels of 1 by 1 meter in a pixel of 10 by 10 meter. So it is not that each of these pixels will be having DN value of 102. They may have values ranging between, say, 105 to 99. Thus, a 100 by 100 meter pixel having DN values of 105, when subdivided into pixels of 1 by 1 meter, will have 10,000 pixels. Now you can see how much large data is now available. There the one pixel was representing 100 meters by 100 meters. Now once the pixel size reduces to 1 meter, then we have 10,000 pixels, and each of these pixels will be having DN values ranging from, say, 114 to 95. Therefore, this image is made up of 1 meter pixel size, and this image will show greater precision or clarity, or will have higher spatial resolution as compared to the image made up of 100 meter pixel size. Now resolution in a photograph is termed as the ability to distinguish two points as separate structures or features rather than a single fuzzy unit. So the term spatial resolution refers to the number of pixels utilized in the construction of the image. Images having higher spatial resolution are composed of greater number of pixels than those of lower spatial resolution. We can thus precisely identify or differentiate between closely resembling objects in an image of higher spatial resolution or an image which will have more diverse gray values. This is a example to show what difference does an image having a smaller pixel size have on the quality of image. Here the image is of 80 meter resolution. That means each pixel size is of 80 by 80 meters. Now we can see that in this image there are no sharp boundaries which are visible. We find that there are some objects which are distributed in the area, but we cannot clearly differentiate between the individual objects. It is just a very fuzzy and the picture is not quite clear. Now if we have an image of the same area with 30 meter resolution, that means here the pixel size is 30 meters, 30 by 30 meters. Now here again we can see that the quality of image has improved and we can differentiate. These are some linear, some sort of roads. These are some areas which are having different shapes and sizes, and they can be, we can see, like here you can see that these red spots, there are two areas divided by some linear, say, road or something like this. Now this image, if again it is taken at a or imaged at a 10 meter resolution. Now in this 10 meter resolution, that means the size of individual pixel is 10 by 10 meters, and for each of these 10 by 10 meter we are having different digital numbers or different reflectance values, and the quality of image has drastically improved. In this we can see that there's some water body, some water boat, etc. is moving here, which is not identifiable here. And then we can differentiate, like this object here, this thing is not visible in this, it is still not visible, but here we can clearly differentiate between the different objects by so now we can understand what is the advantage of having mobile phones which have higher megapixels. We can have certainly better photographs or good quality image in a camera with higher megapixels. So in this, along with the pixels, we discussed about the spatial resolution. We'll be talking about the other types of resolutions in the next lecture. Thank you.